Why are we interested in doing that? We want to assess noise levels. We're interested in frequencies also sometimes. Frequency of noise, in addition to the amplitude of noise, how loud the noise is, can have certain impacts, can affect what kind of equipment we use and how we try and protect workers and so on and so forth. We're going to be using a couple of different kinds of tools. One of these tools, which Mike has right here, is a sound level meter. Okay, and basically, it's just a device with a microphone on the end of it that actually will read out, measure the amount of noise that's present, that's reaching a microphone, and display it on a little LCD display that's on these things. Anybody want to guess what, hazard a guess is what the units are that are on this device that are measuring sound?
Decibels.
Decibels, exactly, decibels. In reality, what we're measuring is the pressure from the vibration in the air, the compression and expansion of the air created by a sound, like a speaker. Sometimes you can actually see like a big woofer. You know, when you got a very low frequency sound, you can actually see it vibrate, pushing air. You know, and you hear that really, really low sound. And that happens with all sound. What's happening is that the air's getting compressed and then expands and compressed and expands. And that compression and expansion passes through the air, okay, and eventually reaches your ears, okay? So it's like a wave on the ocean. In fact, a lot of times, even though it's not really a wave like that, the differences in the pressures can be expressed as a wave, as a graphical wave, okay? On the ocean, just like on the ocean, the actual, if you have something floating in the middle of the ocean, not, you know, by the shore here where you get rip currents and stuff like that, outside in the middle of the ocean, if you have waves, you have like 6-foot wave heights or something like that, the actual water molecules are not moving anywhere. They're just going up and down. The wave is passing through them. If you put something out there and it was floating and there wasn't any wind, but there were large waves, it would just be kind of going like this as the waves pass through it. You know that if you're in a boat, right? Because of big waves, you're bobbing out there, you're not going anywhere, and the waves are passing under you, especially if like you're anchored or something like that. So that's really what's going on. We're sensing that pressure that's reaching our ears. It's a very, very, very low pressure that our ears are sensitive to. It's so low that it's not practical to describe it in terms of standard units, like, you know, PSI, pounds per square inch, right? That's like way beyond, 1 pound per square inch is way beyond the level of pressures that we're dealing with. Even inches of water, like what we used to describe pressure in ductwork and stuff like that, is kind of great. So we usually use metric units like newtons and so on and so forth. So what is pressure? It's force per area, over an area, force over area, right? So pounds per square inch, newtons per meter squared, and so on and so forth, or centimeters squared. We use newtons and pascals are related. I think a newton is like 100,000th of a pascal. So you can actually describe it with these metric units in terms of what pressure that we're dealing with. Problem is that the amount of energy, that minimum amount of energy that our ears can sense, that the lowest sound amplitude that our ears can sense, is like 20 micropascals. And the highest level, at the point where it gets painful and it reaches the limit of our hearing, is like 20 million micropascals. Enormously large range. Very difficult to describe stuff like that. Like, oh, sound in this room over here was 4,567,042 micropascals, and over here it was like 1,900,000. It's very difficult to make comparisons, to discuss it intelligently, and so on and so forth. So instead, we use a system of measurement that's called decibels. Okay, and decibels is what we're taking is those sound pressure levels, and we're converting them using a logarithmic scale. What happens when you take a logarithmic scale? You compress a very large range of numbers into a very small range, much smaller range of numbers. So typically, we're working with anywhere from 0 to 140 decibels instead of that enormous range of 20 million. That really represents the real pressures that we're dealing with. You'll see that it really represents kind of both. It's really not just a log, it's kind of a ratio, and I'll show that to you. You don't have to read for our class. if you're taking noise and radiation, you have to learn all these formulas and so on and so forth. I'll just show you quickly what that relationship looks like. You don't have to worry about actually solving problems with that formula, but just being aware of how decibels are based on this pressure. So we're going to talk about that pretty soon. So here's a graphic that the top part over here shows you what's really happening in the air, the compression, expansion, and compression, expansion, air. And on the bottom is how you would describe that pressure. You know, in other words, positive pressure relative to the pressure, whatever. If I'm silent, whatever pressure is in the air right now, what's reaching your ear when I start talking is alternate higher compression, higher pressure, lower pressure, higher pressure, lower. So graphically, it looks like a wave like that, like a sine wave like that. Okay, so the amplitude of the sound, how loud the sound, is the height of those waves, how much pressure that we're dealing with. The frequency or the pitch of the sound is how many cycles that we have of alternating high and low pressure, right? So how many waves we have. Okay, so 1 hertz, common way of measuring frequency, 1 hertz is 1 cycle per second. Okay, we really can't hear 1 cycle per second. We might be able to feel it as a vibration. We don't hear that. We can hear from say maybe 40 or 50 hertz way up to I don't know, what's about we're going to talk about that, maybe 20,000 hertz if you got really young ears, and maybe 9,000 hertz if you got my ears. You know, so we might even be able to check that right now. So amplitude is what gives us that volume. So the reference level, the minimum amount that human hearing can detect is 20 micropascals. That's that pressure. Okay, so why are we so concerned about that? Well, loud noises, we're going to talk about how our ears work, but loud noises can affect sensitive parts of our ears, damage sensitive parts of our ears, especially if we're repeatedly exposed to them over and over again. We can be exposed to a lot of very loud noises, and we actually can experience temporary hearing loss, but we tend to recover. But if you repeatedly stress that hearing system, if you repeatedly cause a little bit of damage to these sensitive components in your ear, over time you can wind up with permanent damage. Okay, now anybody know what the OSHA standard is, permissible exposure limit for noise in the workplace in decibels?
20.
How much?
90.
I'm sorry, I can't hear.
90 decibels.
90 decibels, exactly. Yeah, actually, technically, it's 85, right? But what is that 85? That 85, if you work in a workplace environment where it reaches 85 decibels, your worker is supposed to implement a hearing conservation program. That involves training you, perhaps supplying you with some protective gear, maybe not, maybe doing medical monitoring your hearing over a period of time every year, sending you for a hearing test, so on and so forth, and examining the workplace to see if he can, reduce your exposure to noise, if you can alter the workplace or make changes to the workplace to reduce your exposure. 90 decibels, you're absolutely right about the 90 decibels. At 90 decibels, you start to get to the point where you have to provide hearing protection and you have to limit the worker's exposure. So OSHA says you can't expose a worker to 90 decibels of noise over an 8-hour workplace, more than 90 decibels noise over an 8-hour workplace exposure. Okay, so that means that if I expose you, if you have a job where you're exposed to the OSHA permissible exposure limit of 90 decibels over an 8-hour workplace day, 4 hours in the morning, take lunch, 4 hours in the afternoon, it's 90 decibels, just right at the permissible exposure level. That means you're not going to have any hearing loss at the end of 20 or 30 years, correct? How many of you believe that? Nobody believes that. It's good you don't believe that because it's not true, right? In fact, it's not a protective standard. It's a negotiated standard with industry and NIOSH and so on and so forth. And in fact, it's not protective. So if you're exposed, even at just the OSHA permissible exposure limit, you're almost guaranteed to have some hearing loss at the end of 20 or 30 years or something like that. And a lot of times it'll be significant hearing loss. So we're concerned about workers being exposed to this stuff. In fact, there's other standards. NIOSH has a recommended exposure limit, which is lower. The American Congress of Government Industrial Hygienists has their own standard and ways of measuring it as well, which is also lower than the OSHA permissible exposure limit. So there's a lot. There's a lot of approaches you can take to this, but the PEL is not necessarily protective. Okay, so now let me get to it. See this graph over here? This graph represents if you generate a noise that has equal amount of energy in all and pressure in all of the frequencies, a very low sound and a very high sound. Most noise is made up of a lot of different frequencies, right? So you go to if you go to the opera and the orchestra plays an overture or something like that, you're hearing the basses, you're hearing the flutes, you're hearing all of them all together. Almost any noise is like that. Even a jackhammer is a number of different frequencies combined. That blue line, that Z line, can you see there's a blue line back there? Yeah. I'm not looking back there, so you got to warn me if I'm saying something and there's nothing. It doesn't have anything to do with what's back there. That Z line represents what we call white noise. In other words, noise that has an equal amount of energy, equal amount of pressure in all of the frequencies straight across the line, right? Now, the thing is that our hearing is not universally sensitive to all frequencies of noise. So if you look at that C band, the black line says C, right? That black line that says C looks pretty much like it's measuring sound levels at all of the frequencies pretty much equally, a little bit at the ends maybe, not quite. But if you look at that A band, that A line over there, what's happening there is that where at the low frequencies, like 60 or 80 hertz, way down on the left-hand side there, even though the sound pressure is up here, it's only measuring it down here. It's measuring much less energy than is really there, right? We use that scale, that A scale, to mimic human hearing because we don't hear things the same across all wavelengths. In fact, we hear it more like this. Our ears are less sensitive to very low frequency sound pressures and very high frequency sound pressures, and more sensitive to sound pressures in the middle. Those are the ones that affect us more. So we discount the very low sounds and the very high sounds when we're measuring it because we want to measure sound levels that are harmful to humans, right? So we don't care about the portion of it that is really not as harmful to us. Okay, so why do you think the middle is, why do you think that section from say 400 to 4,000 is the one that we're most sensitive to? What takes place in that range? I mean, like rock, oldies, rap, what takes place in that range of say 400 to 4,000?
Music, speech.
Speech, bingo, right? Music even much wider range, right, than speech, but certainly speech, communication, right? So we've evolved to have ears that are sensitive in that range, and when that range of sound is affected, when we can't hear that, we are isolated. We lose communication. We're not as safe a worker because we don't hear and communicate with our workers as well, and so on and so forth. So that's the range that we're most interested in. Okay, so you can see here, down at these low frequencies, 125 hertz, we're discounting in other words, we're reducing the amount of, if the energy is up here, we're only measuring a portion of it. Okay, good. Okay, so a couple of the instruments we're going to be playing with today was sound level meters. They just literally are measuring the amount of sound that's in the that's reaching that microphone, the substitute for our ear. And these devices can be programmed. Almost all of them can be programmed to measure in the A scale, the B scale, and the C scale. So if we're measuring worker exposures, what scale are we going to use most of the time? We're going to use the A scale because that mimics that, human sensitivity testing. There's also sound level meters that will actually measure the level of sound at different frequencies. In other words, if you're interested in knowing what the lowest frequency, at the low end, does this noise, is most of this noise being generated at the low end or the high end? Okay, and different kinds of noise will affect you differently, might carry differently. And so you ever like stop at a traffic light, somebody pulls up, he's got his windows rolled up, but you can hear like he's got like 200-watt speakers in the car, and you can hear what part do you hear? Do you hear the high parts? No, you hear the bass, right? You hear that thumping bass and stuff like that. You can't really hear the vocals and the rest of it and stuff like that, because that's what's getting out of the car. That's what's escaping the car, and that's the frequency of noise that you're exposed to, right? And you can actually use these things to define how much of high frequency noise there is present in noise, how much low there is in the noise. Well, we might, in the next 2 weeks, maybe not today, the next 2 weeks, we might be able to spend a little time talking about what that does for you. These devices are called noise dosimeters. We have a bunch of them here. We got little ones like this. What do you think we wind up doing with this little tab at the end? Right, it's a collar, right? Exactly. Why would we want to put it in the collar? We want to measure the exposure that the worker is exposed to. We want to, like an air pump, put it on his belt or something like that, or whatever. We're not going to. We want this microphone within a 2-foot circle around his head. That's the area that we want to measure, right? We don't want to measure, we might want to measure the room, right? We might want to put this in the middle of the room or walk around the room with it and so on and so forth and measure the levels in the room, generally. But as far as OSHA is concerned, and as far as measurements where you're trying to determine whether a worker is exposed above the permissible exposure limit, you always monitor the worker himself. And in the case of sound, you want this within 2 feet of within a 2-foot diameter portion of his head, right? So we got this kind, we got another kind that's got a little thing you put on your belt, a microphone sits up here. And we call these things dosimeters. Why dosimeters? Because not only do they measure the sound pressure levels, like decibels, but they also have little computers in them. And these little computers will actually measure how much noise is the worker's exposed to, say, every minute, store that data, and then as he's exposed to noise during the course of the day, if he's exposed to 90 decibels for 8 hours, it will tell you that he has reached 100% of his of the PEL for sound exposure. If he's exposed to 90 decibels for an hour and 70 decibels for 2 hours and 85 decibels for an hour and so on and so forth, it might tell you that he's exposed to 75% of the permissible exposure limit or 125%. So this will actually convert that into the percentage of the permissible exposure limit that he is exposed to. This one's a pretty sophisticated one. You can also tell it to do A scale, C scale. You can also tell it to calculate the permissible exposure limit using either the NIOSH standard, the OSHA standard, PEL, the OSHA and NIOSH recommended exposure limit, which is lower, the NIOSH recommended exposure limit, the AC, I think even the AC, I think you could, am I wrong about this? I think, right, we can, I think this will do ACGIH also, PLVs, the TLV, right? And that's why this is a dosimeter. That's a sound level meter, only measuring sound level. You set it for the standard that you want to use. Like right now, it's probably set for the OSHA standard, right? You set it for the standard that you want to use. And you set it for the scale you want to use, A, B, or C. Obviously, there might be some applications where we might be interested in using the C scale, but for the most part, we use the A scale. Okay, so we'll be playing around with these. And one of the exercises is that we're gonna maybe a couple of you guys will wear one of these and go find some noise, right? Should be too hard in New York. It can be too hard to find noise. When we used to be at another building, we used to be we used to have those hand dryers. We push them in, like blow high pressure air, high pressure air on you. So we used to send somebody out there wearing it and make them do it for 10 minutes to see what kind of sound levels he was exposed to. Right? And trust me, it's pretty high. Okay, so, all right, so here we are, various kinds of devices like this. There's also, we're also concerned about the environment. In other words, whether we're going to get echo and reverberation, or noise might cancel out, or you might get addition of noise as you get echoes. Okay, there's a hearing protection standard. One of the ways that we can use there's something called an exchange rate. Okay, in the OSHA standard, the exchange rate is 5 decibels. Okay, I think it's 5 decibels. Yes, it is 5 decibels. Am I right? Yes. Yes. Let me think here. 8 to 4. It's 5 decibels. In the OSHA exposure limit, it's if you don't have this available, if you don't have very sophisticated devices available, you could download, on these, even on sound level meter, you can probably store a reading every minute, and you can download it to software, and you can calculate the exposure over 8 hours, and so on and so forth. We haven't always had these kind of tools available to us. Back when, when I first started getting into this stuff, I don't know what we used. Right? Probably just used our ears. Sounds too loud to me, or something like that, or sticks and stones or something. So at any rate, but now we have all these sophisticated tools. But in situations where you don't have these available, but you do have a sound level meter available, you can estimate the worker's exposure by using this exchange system. So basically what it means is, we said already that if a worker is exposed to 90 decibels for 8 hours, he's reached the OSHA permissible exposure limit. Well, let's say if I go up 5 decibels to 95, we use this exchange rate of 5, this doubling rate of 5. If I go to 95, he can only be exposed for 4 hours. If I go to 100, he can only be exposed for 2 hours. Go to 105, he can only be exposed for 1 hour. How can we use that? Well, let's say a worker is exposed for an hour at 100 decibels. He's allowed to be exposed for 2 hours, so he's used half of his dose up if he works for 1 hour, right? That means he can work, if he's been working for an hour at 100 decibels, well, now he can only work, let's see, 4 hours would be 95. He can only work for 2 hours at 95 decibels, because that's half of the dose he's allowed to have. So you can make these exchanges. You can exchange, if you can't reduce the amount of noise in the worker's environment, you can get the worker to only work a limited amount of time in these noisy environments. And you can use this table to determine where you are in terms of like how much of a dose he's been exposed to during the course of the day. So you can limit his exposure, give him other tasks to do, exchange workers, workers have workers exchange tasks, and so on and so forth. We're going to talk about hearing protection. These devices, for instance, these earmuffs, they have, each one of them has a different level that they can protect. Did we bring the earplugs? Okay. And those, each one of these things has the manufacturer rates them for how good they are protecting you from noise. This one doesn't have a tag in it, but the model number is a tip-off. It's called the Blocker 26 cap. This has a noise reduction rating of 26 decibels. That doesn't really mean it really reduces the noise 26 decibels if you're wearing this. There's a calculation you can do to discount that discount. We'll need that noise later on. Keep that around. So we'll have a, what was that anyway? You don't know? Huh? Something fall off the deck. That's okay, don't worry about it. We'll be making plenty of noise. So 26 decibels. While I bring that up, the other thing you can set this for is for slow response and a fast response. What it does is you can tell it to take a reading every like 100th of a second or every 10 milliseconds or something like that. Or you can tell it to take a reading averaged over 1 second. And an environment where you would use slow response would be one where you don't want it to just, if something happens, a book falls on the floor and makes a gigantic noise. You don't want that to overweight what's really going on. So if we wanted to avoid something like that influencing our reading, we put it on slow response. Also, slow response is nice because you can actually read the number that's on there rather than having it flashing all over the place. So at any rate, this has a standard, noise reduction standard, and we'll talk about how we can tell how much this will reduce the worker's exposure to noise. In other words, if it's 100 decibel noise, will this get him below 90 decibels so that he can work in that environment for 8 hours, right? Will it give him that much protection? So, and these little earplugs, right? They have a noise reduction rating as well. Believe me, it's more than you would think. In fact, these noise reduction rating for these, I think is 29, for this is 26, right? Because this is cheap. This is not a real good earmuff, right? But that's the earplugs, yes.
Yeah, are they exactly similar to the one that's selling the market?
Yeah, yeah. Oh no, those may be fitted or something like that.
I think one because my little girl does smell a lot.
I gotta tell you, in my other life, before I retired from my day job, my other life, I did a lot of training and stuff like that. And I used to have like a lot of equipment around. And I had a box, it must have been, I don't know, must have been like 10 gross of these things, for like everybody in the company. And these guys would go out in trucks, they would service air conditioning systems and stuff like that, water systems, really. They would go out on the road all the time. And they would be in mechanical rooms and very noisy and stuff like that. So every couple of weeks, they'd come up, one of them come up, they'd grab a handful of them, they'd throw them into the glove compartment. So they would have them and stuff like that. There was one guy, he was in my office every week grabbing a handful of these things, right? So finally one day I said, hey, Glenn, what's with the earplugs? You use like 10 times as many as anybody else that works here. Turns out he snores. He was giving them to his wife. That's the God's honest truth. I can't make that up. So at any rate, yeah, it's a noise reduction rating. So we're going to talk about that because you can't just use that number. And I don't necessarily mean we have to talk about it right now. We'll talk about it next week because I want to start doing some stuff. Okay, so I'm at this stage. Okay, let's see. At this stage, I think it's a good time to maybe start talking about what our tasks are going to be, or what our exercises are going to be, and which maybe see what we can get done today. So let me open up this document that you guys are holding. Okay, I'm going to increase the view on here. Okay, so I have 8 exercises on here. A couple of them are things we don't really have the equipment for, so they're really we're going to simulate them. I'm going to talk about what we would expect the result to be if we actually had the equipment. So the first thing, imagine that you are not masters of public health and you have real jobs like environmental and occupational health scientists, right? Instead of your administrative jobs, which we don't really look at that as work in our business. So at any rate, let's say you actually have to be the guy who go out there and do these measurements. What's the first thing you do before you start measuring anything? Calibrate. In the case of OSHA noise exposure measurements for visible exposure limit, you calibrate before and after you take any readings. So that would even be now you have to make decisions sometimes, like for instance, if you are in a situation where a worker has a 8-hour workday, right? But that includes a 30-minute break for lunch. But he works 8 hours, works 7.5 hours, but he's got a 30-minute break for work. Well, you're measuring over an 8-hour workplace exposure. You might consider leaving this on the worker for the entire 8 hours. If a worker works 8 hours and he works 8.5 hours with a half-hour work break, then you might consider, I want to measure 8 hours for this his 8-hour exposure. In that case, you would probably take morning readings, stop it, pause it, and then take readings in the afternoon. And you should really calibrate. Anytime you start and stop on this stuff, you want to calibrate these things. Okay, sound level meters, you want to calibrate. Matter of fact, let's do that exercise right now. And Michael demonstrated. We have a sound calibration device. Okay, and this is a unit that literally comes with the instrument. And it has a little hole in the top, and it's got a little speaker in it. And it's calibrated to a specific frequency. right? And a specific amplitude, specific loudness. And it says it usually on the bottom or the side. It actually tells you what the frequency is.
It's 114 decibels at 1,000 hertz.
114 decibels is close to the pain level, close to being painful, right? So it's really loud. Don't stick this against your ear, okay? So, you know, you can hear it. You could hear it from out there. It's really loud. So it actually, you need this right size collar. So you can, notice he pulled the windsock off it, your wind collar or windsock off of it. That's there to, remember, we're measuring sound pressure levels, and some of these sound pressure, we're talking, there's very little pressure differences. So me blowing on my hand is far more pressure than is involved in the sound that we're listening to. So that wind, wind or a lot of air currents and stuff like that can really throw off our measurements. So that's why we often will use, unless it's really pretty much still air, we'll use whatever collar, wind collar. So you want to give it a shot, see what you read?
So they all have different calibration menus.
Oh, no, you just read it rather than, yeah, just read it. Hopefully it'll just be right anyway. What does it say?
113.7.
And it's 114, right? That's pretty good calibration, right? It's pretty good. Technically, there is another way to calibrate. Legally, sometimes you might have to have 2-point calibration of 2 devices like that. If you are a certified industrial hygienist, you get involved in a lot of legal work. And you wind up on the stand testifying about measurements that you made. I guarantee you opposing counsel is going to say, well, how'd you calibrate the instrument? What kind of calibration techniques you use? What does the manufacturer recommend you do for calibration? When was the last time it was sent to the manufacturer? These things are supposed to go back to the manufacturer once a year for servicing and for manufacturer calibration. And so on and so forth. They want to see what records did you keep? Did you write down the calibration?
Your sound, your calibration device, and your sound.
Yeah, both of them.
Pretty much every instrument requires
calibration. So and you have to calibrate every time the sound level meter itself. You use that. The other one is a primary standard. That noise generator. Every time you use that sound level before and after. Okay, to make sure you can depend on your readings. Okay, so first exercise that we have here. Let me get to that. What are you going to do? Each one of you, now we're going to work in teams. 2, 4, 6, 8. We got 10 people. Okay, how about teams of 2? Okay, pick out, 2 people. If you want to work in larger team, you may. But I see that we got 5 of these. We got 10 people. So I think teams of 2 would be good. But you don't have to work that way. You can work in teams of 3 or 4 if you want. So it's not going to take you long to do this. So you can share the instrument, and you don't have to do the same exercise at the same time. We're gonna go through some of the exercise first before we actually start working on it. Okay, so what are you going to do? If you look at that page that you have there, it asks you to put your name down, the date, whichever the date is, like today and next week if we wind up doing it next week, and your other team members, if it's one person and so on and so forth. Now, you put down your other team members, but everybody is eventually going to be responsible for handing in their own version of this. And by hand in, I mean upload onto Blackboard. Okay, not necessarily today. I don't expect that we'll necessarily get done with everything today. Okay, so our first exercise, calibration of sound level measuring equipment, exercise 1. So what I want you to do, I want you to write down the manufacturer, the model number, the serial number of that device. Almost every time you do any kind of measurement in the field, you are going to be documenting the instrument that you use, the kind, the model number, the serial number, so that you can identify that unit if you have to go back and check it. Okay. And what are you going to do? You're going to put down the frequency and the decibel level that the calibrator is set to, and your reading that you get from the actual sound level meter. Okay, and you can use we have 3 of these sound level meters, so you can use those. Okay. Yeah, that's okay. Well, like I said, we're gonna be doing those of you that might do that first, others might do something else. So what's the second exercise? The second exercise is, the third exercise. The second exercise? The third exercise is that 5 students, 1 person in your team, will wear a noise dosimeter for the duration of this show that we're doing here, so that we can see if we actually read a change in the dose. If I make enough noise in here, you might actually be able to see a % or two, by the end of the day. And what do you think of the idea? Maybe sending 1 or 2 people home with them. Anybody work in a noisy environment? A really noisy, a rock band? Nobody's in a rock band. Nothing. No noisy.
Noise levels in your office.
Yeah, or the train. How many times you guys take the train? Yeah. So what's that?
I do play the keyboard in the house. So
What? Oh, the keyboard.
Yeah, sure.
Yeah, if you crank it up high enough, yeah, why not? Okay, so why don't you take one and hang around the subway? And why don't you take one and I'm not, yeah, while you're playing the keyboard and stuff like that. And after a while, just look at, glance at it every once in a while and report back to us. How high did it read? Was it 90 decibels, 80 decibels? In other words, to get a picture of, you'll get a picture of what is 90 decibels. What is this thing, 85, 90 decibels, where we're starting to be concerned about worker exposures on the subway? When do we get to the point where it's that loud? And think about, well, what about that conductor that's on that train all the time? And every time that goes into a train stop, the brakes go on and the noise and the rumbling and so on and so forth. They used to be a lot worse in the old days than they are now. But yeah, think about it as you get the readings and stuff like that. Think about what his exposure is if he's on this, he's doing 8 hours or a double shift of 16 hours, what his exposure really is. Okay, so I think we can afford to put 2 of them out, right? I don't think anybody's working with them. Yeah, I'm going to
check with Brian.
Too late. Okay, it's too late for doing that. Now listen, if the deal is though, I don't think anyone is using these, right, for a project or anything like this. As we get to the end of the semester, one of the things we can do is, rather than have an exam at the end of the semester, maybe we can, as a group, do some sort of project, take sound level measurements, take some other kind of measurements, take soil samples to, look for lead in them or something like that, paint samples. Maybe we can come up with some sort of group project or something like that instead of an exam at the very end of the semester. Everybody's happy about that. Until you see how much work. Wait, you haven't seen how much work a project is, but you guys can come up with ideas. For instance, Jack Caravanos, one of the things he used to do every once in a while is he used to have students take lead dust measurements, and the way that he used to do it is that each student would get like a bunch of wipes and plastic bags and labels and a route, and they would take a bus, like a uptown, downtown bus, and they would run off the bus quickly and take a 1 square foot wipe a 1 square foot area on those glass enclosures on the bus, put it in a baggie, write it up, get back on the bus before it leaves, and then go to the next stop and take another one. So then we would analyze them for lead, and we would see what neighborhoods had higher lead levels in the, when we put the data together, we could examine if areas uptown or downtown how higher lead levels than others. Surprisingly, there is some lead in the dust in the air in New York City. You would think with all the paint, with how careful they are about demolition now and no more leaded gas and so on and so forth, you would think that we wouldn't see much lead.
Still in the soil.
Yeah, still in the soil, for instance, under the bridges and yeah. And in fact, I think then we do one now. Were you with us in one of the classes where one of the guys went out and got a soil sample out of one of these big pots on the street?
Oh, yeah.
And we had, I think there were like 100 or 200 parts per billion lead in that. It was pretty high, so who knows? They might have been contaminated with some paint or something like that, or who knows what was going on with that. But at any rate, so there is still a lot of lead around. Okay, so yeah, maybe 2 guys, you and you, take them home, bring them back next week. The only thing is you got to write down a phone number for you guys so that, like, if Brian says, shit, I need those things, you can bring them back in, okay? That's the deal. I'm going out on a limb here. I don't think he'll object. I don't think he'll object. He'll just say something like, if they don't come back, Tony, you're paying for them. That's okay. So at any rate, okay. So a couple of you guys are aware of these things. So that's our second exercise. A third exercise is I am going to set up a little speaker, and I have on my phone somewhere, I think I have on my phone somewhere, I can create a white noise coming out of this. And anybody ever use one of those little things where you put it alongside the bed, you can make the ocean and birds and stuff like that. And isn't there always something there that says white noise? You can select white noise. It's kind of like a nice even hiss. That's white noise. Okay, and we'll create some white noise, a little bit more, enough at least for you to measure with the sound level meters. And I'm going to ask you to measure it with the sound level meters using an A-weighted scale and a C-weighted scale. So if you go to back to our table here, right, there's our personal monitoring that does dosimeters. We can share the data when these guys come back with it, or what, maybe we'll find some now. Sound level exercise 3, right? We want to know, well, if you keep the same distance, write down the distance you are from that sound source. And actually, I think I have a tape measure distance. It might be still in the bag or something like that. It's around here somewhere. But, oh, okay, yeah, there it is. Measure 5 feet from the speaker or something like that. So you're at exactly the same distance when you do this, right? And measure with the same device, measure with it set to the A scale and measure with it set to the C scale, right? And then think about, well, which of these two is going to read? They're not going to read the same for both sounds. Both scales are not going to read the same number, presumably, if it's a really white noise. Try and figure out which one you think is going to be a higher number, which one's going to be a lower number, and then actually measure it. Okay, so that's exercise 2. That's 3 rather. Exercise 4, noise reduction with distance. Okay, now one of the deals here with any kind of energy. Okay, guys, look up for a second because I want to use my hands here to describe this. Any kind of energy. If you produce that energy from a point and it's radiating out, right? Okay, so imagine this energy, there's a certain amount of energy coming off of this thing, and 1 foot away from that point source, from that source of radiation, that source of noise, that source of energy, whatever kind of heat energy, whatever it is, if you're 1 foot away, then that energy now, instead of being in one spot, is on a surface of a ball that's 1 foot in diameter, right? Okay, so now if I go out to 2 feet in diameter, right, now that energy is diluted because now it's spread out. It's not same amount of energy as started here, but now it's spread out to 2 feet. So what is the formula for the surface of a sphere? Anybody remember? No, that's a circle. I think it's 4/3 pi r squared, right? 4/3 pi r squared. Okay, so what is that? What is the r squared? As the radius doubles, the size of the surface is 4 times. So in other words, what would you expect if we measure the sound pressure level at 2 feet and it's 100 decibels, right? What would we expect at 4 feet? We would expect to have it's double the distance, so double the radius, so we would expect 1/4 of the amount of energy that's reaching that device. And at 8 feet, now, so then we would expect 1/4 of that. Okay, well, what is 1/4 of that? Remember, we're doing a logarithmic scale, right? So you guys don't know, you're going to measure it, and next week we'll talk about what it should be, right? So we're not going to give away the answer to that. You guys will actually measure it. So in other words, measure it at 1 foot from this noise source, then use the ruler, measure it at 2 feet, 4 feet, 8 feet, 16 feet, and see what you get when you measure with the sound level meter. And then next week we'll see what it should have been theoretically. And where are you going to put that? Well, we got a little area over here for exercise number 4. 1 foot from the source, 2 foot, 4 foot, 8 foot. 8 foot as far as we're going to go. Okay, yeah, I don't want to do 16 feet because we'll have so much, we'll have to make it so loud. I'll drive, we'll never be invited back to this room again. And I want this room. Okay, so extra noise reduction from an enclosure. I meant to bring a box, but okay. So one of these dosimeters has a remote microphone on it. So this dosimeter does the same thing that the other ones do, except that this, before we got those things, which, have lithium batteries, and they'll work all day long. This is an older one, which uses NiCad batteries. They're very heavy. They're so heavy, you're not going to wear them on your collar. It's got to go on your belt, but we got to measure up in the hearing zone. So they would put a remote microphone on it. Well, the good thing about this is that we can use this to measure the level of sound. We'll drop a box over a speaker, measure the level of sound inside the box, measure the level of sound outside the box, just an inch outside the box, right? And see how good is that enclosure at attenuating the sound. Silly exercise. However, it demonstrates that one of the things that you can do to protect the worker is to put the sound in the device that's causing the sound, the noise, in an enclosure. That's one of the many engineering solutions they can use to protect the worker. So we're going to give that a try inside and outside of the box. Even though it's kind of a hokey kind of demonstration, and if you go back there, there's a place for you to put that data, 2 numbers inside and outside the box, just to demonstrate that it actually works. Of course, how about this? Is using an enclosure, putting an enclosure around the sound source. Is that the only way you can use an enclosure to protect the worker? How many of you guys have ever been in a big power plant, like a Con Ed plant, or anybody ever been in something like that? They have, what's that? Yes? Did I hear a yes? No? They have, if you go over here to the Con Ed place on Long Island City where they have the 3 big smokestacks, right? They have giant steam turbines. They have giant boilers there. They produce 2,000 PSI, very high pressure steam. And that steam goes into these steam turbines, spins the turbines, spins generators, create electricity. And then that waste steam now is only 700 pounds, and it goes to another turbine, spins that, and then it comes out 300 pounds, goes to another one, and then it goes down to 125 pounds. And now it's not really useful to spin turbines anymore. What do they do with that waste steam? Anybody know? From that plant, they pipe it into New York City underground. And almost all the buildings south of 57th Street in New York City, a few north of there, instead of having boilers for heat in the wintertime, they use that steam for heat in their buildings and hot water in their buildings. Ever notice that every once in a while you'll be driving around the street and there's steam coming out of the ground, right? Where do you think that is? That steam pipe's not leaking, right? What's happening is that groundwater is hitting that 120 PSI steam is 250, 300 degrees, right? Because it's under pressure and get hotter than 212. So when groundwater or rainwater hits that steam pipe and the insulation is cracked or open or something like that, it flashes off the steam and you get that plume of steam coming out of the street. And anybody ever wonder why they put those pipes in the ground and it's coming out of the top? Right? The reason why they do that is because until they can get down there and repair the insulation or deal with the water problem that they have under the ground, they don't want that steam, clouding up the entire street, coming out of a crack and clouding up. So, it looks like an old Batman movie, the Batmobile coming through the cloud of steam or something like that in Gotham, right? You don't want that because it's dangerous. It'll run over pedestrians and stuff like that. So they just capture the steam so it goes up above the site level of the vehicles and stuff like that. That's usually groundwater. If it isn't groundwater, that's a big problem because that's under very, very high pressure. And what happens if one of those steam lines breaks under that pressure? Anybody think, has that ever happened? It's happened several times. Most recently, about 20 years ago, and it killed about 3 or 4 people on 42nd Street and Lexington Avenue. A couple people in a vehicle, I think maybe a pedestrian or something, and it just exploded. The whole street exploded. In fact, it happened more recently than that. In Chelsea, on 5th Avenue, around 23rd Street, they had a steam line explosion, and it blew off the insulation, and that steam line had been in the ground for 60, 70 years. So what is it insulated with? It's insulated with asbestos. So what does that mean that they had to do once that asbestos got off into the air? That means they had to close the street down for days while they hosed down and captured all of that material from that insulation that had blown up onto the buildings and windows and so on and so forth. So it happens every once in a while. So at any rate, getting back to this power plant, I diverged a bit there. Getting back to the power plant, they have these big steam turbines. They're gigantic. They're in these gigantic rooms. They're not going to be able to put an enclosure around them. So what can they do with an enclosure instead? Enclose the workers, exactly right. So in other words, they have little buildings, little little control centers inside the building that are all glassed in, insulated, and so on and so forth. And they're inside of them. So they're all insulated so that it's sound dampened and so on and so forth. So the only time they're exposed to the noise is when they have to go out, leave, and take readings on an instrument or check a valve or something like that. So most of the time they're inside monitoring the operation of the equipment. They're in an enclosure that protects them from the sound that's on the outside. So, okay, yeah, so that's why we're interested in enclosures. Now, 6, we're just going to simulate. That's Octave-Band. I'm going to talk about that now. 7 is earmuffs. Remember we talked about noise reduction rating on here, right? So in other words, one of the things I can do is that we can generate some noise here. And I can put this, I was going to bring in a soccer ball. I forgot to do it. Because to simulate a human head. So, but I can simulate we use our own heads. We don't have to simulate them, but we're going to put them on like that. It's difficult to talk with them on because we can't hear anything. So at any rate, we're going to put it on and we're going to take a reading outside of the earmuff and inside of the earmuff. That's why I was so interested in having this, because this we can actually kind of stick underneath here and it won't seal up perfectly, but we should be able to measure a reduction in the amount of sound outside the earmuffs and inside the earmuffs. Next week, you're going to write down the difference, right? Next week, we're going to look over what we recorded this week, and we're going to figure out how does that relate to this 26 on the noise reduction rating on here, and how does it relate to the you might have briefly saw as I went past the calculation that OSHA requires for you to modify the noise reduction rating to a practical use. Okay, and we will apply that formula and see how it relates to the numbers that you measured. Okay, so what's the next thing? What happens if I have a sound source over here that's 90 decibels and a sound source over here that's 95 decibels? How do they add together? Do they add together? Is it twice as much sound? Is it 50% more sound? Well, what about if this is 100 decibels and this is 90? How does that add together? How about if they're the same? Well, we have formulas that we can use to estimate that effect. We're going to actually measure it, right? And then next week again, we'll actually talk about if we can get through all this. At this point, we might not get to that, but if we do, that we'll do it next week. And if we do, we'll talk about the results that we got and how to actually calculate it. And then finally, 9 is prepare a sketch of the room showing the noise sources. I went by a slide there very quickly. And the idea there, that really might be better waiting for next week, but we'll see. But the idea there is let's say we have a noise source over here, right? And we have another noise source in the middle of the table. And we're simulating a grinding machine here, a milling machine over there. And we want to see how close that a worker has to be to these devices, or what the sound exposure is in the room, depending on where he's standing. And what we can do is we can actually measure, well, if this is one source here, we can measure, well, right here it's 90 decibels. Right here is 90 decibels. Right here is 90 decibels. Right there is 90 decibels. Right there is 90 decibels. Over there it's 95 because we're getting sound from there and sound from here. 95, so now we don't get 90. Where is it 80 decibels? Where is it 95 decibels? We can draw lines that show us where we are, that can help us predict where we're standing, how much sound we're exposed to based on where we're standing in the room when those devices are producing noise. Okay, anybody like to follow the weather? You ever see those lines they put on the weather's barometric pressure lines? Like, in other words, you have all these little lines, squiggly lines next to each other. Or if you hike. Anybody here a hiker? What do you guys do at spare time? You're not hikers. If you're a hiker or something like that, topographic maps to have a wiggly line, and it'll say 600 feet. And then the wiggly line, it'll say 500 feet. Another wiggly line, and it shows you if they're close together, it means that it's steep, right? If they're far apart, it means that then it's not so steep, right? So those are lines that show you the elevation. Same kind of thing, except we're talking about what the noise level is at any point. And you can use them the same way as if you pass that line, you know that you are in an area where the noise level has gone up. Right? So we'll kind of work on that and try and sketch it out. Maybe not today, but maybe. Okay, so let's take a 5-minute break, get the noise set up, and then start measuring stuff. Okay, and you guys choose teams. Like I said, we got enough equipment for teams of 2. If you want to go into team of 3 or 4, that's fine. But you guys get together and choose your own teams. Okay, and one big team. No. I want you guys to do your own. I want you guys at least I want you to put your hands on these instruments. This is your opportunity, right? Especially public health. You may not be able to get this opportunity again to play with these toys. Right? You remember the Batman film that with the Joker, the one that Jack Nicholson was in, right? Where Batman is showing up with these airplanes and these boomerangs. Remember what line he used in that? Where does he get all these wonderful toys? Right? That's you. This is a chance for you to see, play with all these wonderful toys that environmental occupational health specialists play with. Right? So okay, good. So let's take a break, a 5 or 10 minute break, and we'll get the noise set up.